Hello viewers, in today's class we are going to discuss yet another important and very interesting application of Rolle's theorem in theory of equations, right? So here we'll see a direct application of Rolle's theorem in the form of a problem, right? So here we have a problem in which we have to prove that if p of x is a polynomial, then between any two roots of p of x is equal to 0 lies a root of p prime of x is equal to 0, right? So we'll see this problem with the help of Rolle's theorem. So let us first see what exactly this problem is all about, right? Now see, if we have a polynomial that is p of x, right? And if this polynomial, if we form an equation with the help of this polynomial p of x is equal to 0, and if this polynomial has two roots, right? Suppose this polynomial equation, that is p of x is equal to 0, it has two roots, say alpha and beta, right? Then this problem says that we have a root of this equation, right? Then we have a root of the derivative of p of x is equal to 0, which lies between these two roots, right? Now suppose if we have a root, say gamma, right? If gamma is a root of this equation, that is p prime of x is equal to 0, then we have to show that this gamma, it lies between alpha and beta, right? So this is exactly this problem is all about, right? So let us have a more clarity of this problem with the help of an example, right? So let us take a polynomial. Say p of x is equal to x square minus 3x minus 10, right? So here we are taking a quadratic polynomial, right? So here the degree of the polynomial is 2. So prove that if p of x is a polynomial, so here we are taking p of x as a quadratic polynomial, right? Then this problem says that then between any two roots of p of x is equal to 0, right? So let us form an equation with the help of this polynomial. So p of x is equal to 0 implies x square minus 3x minus 10 is equal to 0, right? So now being a quadratic equation, this equation must have two roots, right? So let us denote these two roots by alpha and beta, right? So here we have assumed the two roots as alpha and beta, right? Okay, now let us find the values of alpha and beta by actually solving this quadratic equation, right? So we can do this by splitting the middle term. So we have x square, and then we have minus 5x plus 2x. So we have minus 5x and 2x as the two factors, and here we have minus 10 is equal to 0, right? So we can now write this term as x minus 5. Then we have 2 common, we have x minus 5, and then we have x minus 5, and x plus 2 is equal to 0, right? So now we have x plus 2 is equal to 0 and x minus 5 is equal to 0, right? So from here we have x is equal to minus 2, and from here we have x is equal to 5, right? So now we have two roots as minus 2 and 5. So let us take alpha as minus 2 and beta as 5, right? Okay, now see, this problem says that if we have any two roots of p of x is equal to 0, then there must lie a root of p prime of x is equal to 0 between the two roots of this equation, that is p of x is equal to 0. So now let us differentiate this equation, right, or this polynomial. So p prime of x is equal to the derivative of x square minus 3x minus 10. So we have 2x, the derivative of x square is 2x, and the derivative of x is 1. So here we have simply 3, right? And the derivative of 10 is 0, being a constant, right? So we have p prime of x, which is dp over dx, that is equal to 2x minus 3, right? So let us form this equation, that is p prime of x is equal to 0. So we have 2x minus 3 is equal to 0. So x is 3 over 2, that is equal to 1.5, right? So the root of this equation, that is p prime of x is equal to 0, is 1.5, right? So the value of gamma is equal to 1.5, right? So now this problem says that if p of x is a polynomial, then between any two roots of px is equal to 0 lies a root of dpx over dx is equal to 0, or p prime of x is equal to 0, right? So now see, we have alpha minus 2 and beta as 5, right? So here we have alpha, this is minus 2, and here we have 5, that is beta, right? And 1.5, it obviously lies between alpha and beta, right? So this is gamma, so this is 1.5, right? So 1.5 is greater than minus 2, but it is less than 5, right? So this is all about this problem, right? But here we'll now see the proof of this problem with the help of Rolle's theorem. So let us first quickly see the formal statement of Rolle's theorem, right? Now see, Rolle's theorem says that if we have a function, say y is equal to f of x, then and this function is defined in some interval a comma b, then if this function is continuous in the interval closed interval a comma b, and this function is derivable or differentiable in the open interval a comma b, and the third condition is that f of a is equal to f of b, and if a function satisfies these three conditions in the interval a comma b, then Rolle's theorem says that there must exist a point c which lies between a and b, such that the derivative of this function at this point c must disappear, right? Or it must be equal to 0, right? So this is the statement of Rolle's theorem. So for this problem, let us take the function as y is equal to p of x, right? And here we are given that p of x is a polynomial function, right? So since all the polynomial functions are continuous and differentiable, right? So we have the polynomial equation as p of x is equal to 0, right? So this statement or this problem says that if p of x is a polynomial, then between any two roots of p of x is equal to 0, right? So let us assume that p of x is equal to 0 has two roots, alpha and beta. So let us form the interval as alpha comma beta, right? So p of x is a polynomial function. So obviously this function is continuous in the closed interval alpha comma beta, and this function being a polynomial function is also differentiable in the open interval alpha comma beta, right? And moreover, since alpha and beta are the roots of this equation, so alpha and beta must satisfy this equation, that is p of x is equal to 0, right? So taking x is equal to alpha, here we get p of alpha is equal to 0, and taking x is equal to beta, we have p of beta is equal to 0. So from these two equations, we can see that p of alpha is equal to p of beta, right? So all the three conditions of Rolle's theorem are satisfied by this polynomial function p of x, right? And p of x is equal to 0 has two roots alpha and beta, right? So now Rolle's theorem says that there must exist some point, say x is equal to gamma, which lies between alpha and beta, such that p prime of gamma should be equal to 0, right? So we see that there is a number gamma which lies between alpha and beta, such that the derivative of p of x at this point, that is x is equal to gamma, it must be equal to 0, right? So p prime of gamma should be equal to 0, and this equation suggests that gamma is a root of this equation, that is p prime of x is equal to 0, right? So this real number gamma, which lies between alpha and beta, is a root of p prime of x is equal to 0, right? So in our example, which we have taken for the illustration purpose, we have the quadratic polynomial x square minus 3x minus 10, right? And we had alpha is equal to minus 2 and beta is equal to 5 are the roots of this equation, right? That is p of x is equal to 0. So we have the interval that is minus 2 to 5, right? And we have seen that minus 2 and 5 were the roots of this polynomial, right? So p of minus 2 is equal to 0 and p of 5 is equal to 0, right? And when we have taken the derivative of this quadratic polynomial, that is p prime of x, that is 2x minus 3, then we have seen that x is equal to gamma gives us p prime of gamma is equal to 0. So we had 2 gamma minus 3 is equal to 0. So gamma is 3 over 2, that is 1.5, right? And 1.5, it belongs to the interval minus 2 comma 5, right? So this quadratic polynomial satisfies all the conditions of Rolle's theorem.